So I'll present my work Xproof, as Mihal mentioned, and I forgot to mention that this was accepted last year at ICML. Yeah, this is joint work with Evan and Dan at Stanford and my advisor Kamalika at Meta now. So yeah, I think this crowd does not need to I don't need to give it much introduction about explanations. Yeah, but I'll still say something. So we have AI models. Usually they are black boxes, meaning we don't understand why they make certain predictions. But explanations have been sort of seen as a tool to open the black box. So given some prediction, they can give us some insight into why this particular prediction was made. And there are multiple use cases of explanations. The most popular one being debugging by model developers. So, model developers can find spurious correlations, for example, that is being used by the model to make predictions. And in this paper, they found that the model used things like some text on the x-rays to make predictions about classifying the image as like disease or benign. But another interesting use case of explanations that we will explore in this talk is to use as justifications. For example, model developers can use predictions to justify certain things to customers. They can justify that the model is fair to the customer, or they can use explanations as a way to satisfy regulations, such as EU's right to explanation. And they can also use explanations to sort of suggest recourse to change outcomes. So essentially, here explanations are used as a trust enhancing tool by model developers to users. But there is a big problem here, which is of misaligned incentives. Model developers are incentivized to return incontestable explanations rather than give two explanations of two true workings of the model. For example, suppose a bank is using a machine learning model to make predictions about loan applications. And suppose it rejects the loan application for a person. And the true explanation might be that the model is using gender to classify. But this is obviously an unfair, this obviously shows that the model is unfair, and the user can go to court if they get such an explanation. So the model developers are instead incentivized to say something like the loan was rejected because your salary is low. And here the user will think that, oh, it's some problem is with me and I should try to get a high paying job. So this is sort of like an incontestable explanation that model developers are incentivized to give rather than reveal this true explanation. So, what allows model developers to cheat in these scenarios? The first one is that models are kept confidential. So, users on the other end are never going to be able to see what is the model that a bank, for example, Bank of America, is using, right? They would never open source it. So, this allows model developers to swap the models as and when they like. For example, they can use different models for generating predictions versus explanations. And they can also swap the model for specific inputs, for example, for a particular gender or a particular race. Or they can also change the model post audits. So, in the auditing process, it might be found that the model is fair, but nothing stops them from changing the model post audits. And for the first two cases, there's also, like, I forgot to mention, but there's also literature which shows that this can be done adversarially without being caught. So models can be changed for specific races, or for they can use different models to generate predictions versus explanations without being caught by auditors. And another reason why model developers can give different explanations is because the explanation calculation is hidden. So somebody on the outside, like a user, does not know what algorithm is used to run the explanation generation, or they don't even know what are the hyperparameters which are used in the explanation algorithm, and they also obviously don't have access to the model, so they can never check that the explanation that is given to them is indeed correct or not. And there are some methods like consistency checks that are possible here, but in those cases, for example, like multiple users can look at their responses, their inputs, and their predictions and try to see by some consistency checks if they all match or not, right? But it has been shown to be NP hard, and that process also puts the onus of checking the correctness of explanations on the users, and it makes the model developers still accountability free. So these are the problems with the current paradigm. And there has been some work which shows that explanations fail to achieve their purpose in such adversarial contexts, and maybe we should stop using them. And my work is sort of saying that probably there is still some hope if we use cryptographic tools. Yeah. So this is the basic setup, and I hope everybody understood it. But I think we wanted to take questions in the end. But if there are some clarification questions until now, I'm happy to answer those. Okay, probably there aren't. So I'll just move ahead. Yeah. And now I'll take a bit of a detour to explain the cryptographic tools used in our paper. So the two cryptographic tools are commitments and zero knowledge proofs. For commitments, suppose there's a bank which uses a model with weights W. Commitment is a function which creates a string out of the model weights. Suppose it's like com underscore W, and this commitment string is broadcasted by the bank. So it's put up on like GitHub or elsewhere. So what this commitment does is it connects your weights to the string, and there's like it's a binding property. And secondly, it doesn't even leak the private model weights W through the commitment string. So the commitment string is not leaking anything about your model weights. So these are the properties of commitments, and this is like a one-time thing that is done before model deployment. The second tool is zero knowledge proofs. In this proof setting, there exist two parties, the prover and the verifier. The prover is, in our setting, the bank, which holds this confidential model, and the verifier is the user. And they both have access to a circuit P, which in our setting is an explanation algorithm which is written in a ZKP library. The prover has input model weights W such that the circuit of W is 1. And what the setting allows us to do is it allows the prover to convince the verifier that P of W is equal to 1 without revealing any information about W. So what we want to maintain in all this setting is that like the bank holds the model and it never wants to leak the model to the user, right? It wants to keep the model confidential. But at the same time, we want to give the verifier some tools to verify the explanation and the prediction that it's getting from this hidden model. So that's what we're trying to do here. And ZKPs sort of enable that. So what happens is the prover gives a cryptographic proof pi to the verifier, and the verifier checks this proof using the commitment string that I discussed earlier. And what it does is if this proof passes the check for the verifier, it means that the explanation that the verifier received from the prover is correct. and without it's calculated without any manipulation. It comes from exactly the model that was committed to. um, yeah, I hope that's clear. I'll come to this later, but what are the guarantees that we are trying to give here? So the guarantees using zkps are that the same hyperparameters are used for all inputs. Then the prediction and the explanation are generating using the fixed model that we initially committed to. And the generated explanation is calculated correctly without any manipulation. And all this happens while the model is still confidential. So this is what we are trying to get to with the cryptographic tools. Yeah. And to explain the protocol xproof, so initially the model developer commits to the model, and this happens before the model is deployed, and this happens only once. And after that, during runtime, a user comes in and they submit a query, example, a loan application to the bank, and then the bank returns an inference, that is the prediction of accept or reject, and an explanation, which is like a regular explanation, and then it also gives a cryptographic proof in addition to all of this, which can then be verified by the verifier. And as I mentioned, like the first property, that the same hyperparameters are used for all inputs, they also come from commitments. So you can also commit to hyperparameters. And then the commitment string is used in the proof and the verification of the cryptographic proof of so that's how, like, it's the model gets tied to the explanation and the inference. And because of the verification of the proof, you can know whether the generated explanation is correctly calculated or not. And neither zkp nor commitments are leaky, so the model confidentiality is still maintained.
There was a clarification question on the chat.
Yeah, I can't see that.
So is pi an explanation?
Right, so pi is a cryptographic proof of the explanation. So it's generated using the zkp library. Yeah, but it uses the explanation.
Okay, I hope it answers the
Yeah,
question. Thanks.
yeah. Are there any other questions I can answer?
Well, actually, I have a question.
Yeah.
So in your protocol, P is a binary function, right? The circuit, but the explanation algorithm would not be binary.
Right. So what we want to say here is that so this is PW comma explanation equal to 1. So what we are trying to say is the explanation, for example, you are a female, or your salary is low. P of W is saying that, like, that explanation is correct. So I'm writing bad notation here, but what it means to say is, if P of W comma explanation equal to 1, it means that the generated explanation is actually the real explanation.
Okay, thanks.
Yeah, and what is the explanation method that we use in the paper? So we use LIME. It approximates local decision boundary around an input X with a linear one. So the original decision boundary can be nonlinear, but we're trying to approximate it locally with a linear function. And the weights of the linear classifier are used as explanations in LIME. And this is like a very simple view that we are using. So the way Lime works is, given an input X, you sample n points around it, you weigh them according to distance from the input point, and you get predictions for these sample points according to the model F, and then you fit a weighted linear model using the sample points. and you return the linear model weights as the explanation. All right. And what are the challenges to doing this? So the main challenge is that you have to implement your explanation algorithm as a circuit in a ZKP library. And this circuit is meant to sort of check if is meant to sort of generate a proof for the explanation. But these libraries are different from ordinary Python or like C++ libraries. They don't work with floating points, and they only allow arithmetic operations, and they also don't have any support for optimization solvers. So yeah, the major thing here is optimization solvers, because you have to train like a linear regression or whatever model, right, to get the linear model basically. Uh, so instead of re-implementation, we use some strategies, such as you can use like duality gap or checks or some closed form checks to instead of checking that every step of the optimization solver is correct, we can verify that the end solution is correct. Basically, that's what we are trying to do here. And like, just to give an overview about circuits, so basically in circuits what we are trying to do is we can either, like, whatever, for each line of lime, we want to check that each step's output is correct or as expected. So one way of doing that is you do the entire process, right? So if you want to sample endpoints around the input, you, like, whatever is the Python code to sample endpoints, you repeat that exactly in the circuit. And if the answers match for each step, then you know that, like, the Python code is run correctly, there is no manipulation. But another way to do that is you just verify that whatever the Python code has outputted, it's actually correct. So for some things like step 4, we can use the verification strategy. And for some things like the step 1, we can actually test the code line by line, like transform the code line by line into a ZKP circuit. Yeah, I hope that was clear, but I can clarify any doubts if there are. And so resulting, like, we write some 3.5K lines of code to transform the algorithm into a circuit. And another challenge is that ZKPs introduce additional computational overhead. So, like, usually they are very, very slow. And in our paper, we are only able to we run it for small neural networks, and we also run it for some random forests, but it's not like LLM scale. And yeah, so one solution to reducing the ZKP overhead is to engineer ZKPs like very closely so that we make them very efficient. But another way is that we modify the explanation algorithm itself to make it more ZKP amenable. And that's because, like, these ZKPs, they're obviously not designed for anything ML related stuff, right? So that's why they tend to be slow for ML tasks. So we are approaching it from the other end of the spectrum. We are trying to modify our ML algorithms to make them more ZKP amenable. And as we can see in Lime, there are these 3 steps that get repeated a lot. So you have to sample a point, you weigh it according to the distance from the original point, and then you get predictions for this sample points from the original model. So you do these 3 steps n times. And if we can do some savings here, then probably it helps. So we did some, like, very simple tests here. So for sampling points, you could use we found 2 types of methods in the literature. You could either use uniform sampling or Gaussian sampling, and accordingly you can use like exponential kernels, or you can use no kernels to get the distance. And this results in 4 variants. Basically, you sample Gaussian with exponential kernel for weights, Gaussian with no kernel, uniform exponential, and uniform with no kernel. And what we want to test here is that is any of these 4 variants more ZKP efficient than others? So we have different traditional data sets like all tabular, and we use different small neural networks and random forests as models. And the first question we want to see is, do the different variants of Lime produce equally good explanations? So we have a metric that I forgot to mention. It's prediction similarity. So how similar are Lime predictions compared to the original model predictions? Because Lime is like the linear classifier. So how similar are those predictions to the original model predictions in a neighborhood? So that's our metric on the y-axis, and on the x-axis we have our different data sets and the different variants. So G is Gaussian, U is uniform, and all of that. So we see that almost on all the data sets, the explanations are equally performant or like equally good or equally bad, whatever you want to call it. So there's not much difference in the quality of the explanations, no matter which variant you use. But in terms of ZKP computational overhead, we do see some significant difference. So we see that, like, so there are 2 parameters to computational overhead. One is proof generation time, which is mostly the one that takes the larger chunk of the computational overhead. And this proof generation is done by the bank. So we see that in our experiments, the most amount of time is taken by the Gaussian plus exponential variant, which is around 1.5 minutes. And the least amount of time is taken by uniform plus no kernel variant. And it's like 0.5 minutes, around 0.5 minutes lesser. And for the verification time, it doesn't matter that much because it's in the order of seconds and it's already like 0.1 seconds, but we see some similar trends. Yeah, and another aspect of computational overhead is proof size. So the proof size is also following similar trend as the proof generation time, and we see that it's on the order of like some 10 kilobytes or something. So it's not very huge to begin with. Yeah, so that is, I wanted to keep the talk short so we could discuss more, but this is basically the talk. And the summary is that we are we are operationalizing explanations in adversarial contexts where there are misaligned incentives with cryptographic tools. And we provide a sort of full stack solution. It works end to end with like confidential models, and we show how you can make the compute overhead more manageable. And in the paper we added additional experiments showing ablations for like how does the compute overhead increase with model size and so on. Yeah, and some open directions to this could be, how do you scale these to bigger models and different explanation techniques? And more interestingly, like, are there other scenarios, especially in the LLM era, where ZKPs are still useful? Like, can you basically you look at ZKPs as a trust enhancing tool? So are there other properties where this trust enhancing tool can be useful? Yeah, and that's it. Thank you.